Hi, the topic of this video is scalar triple product. That is a very important topic for JEE. I'll probably say this is the most important topic for JEE, more than cross product, more than dot product, because this combines both cross product and dot product. There are a lot of questions which come in JEE just based on scalar triple product. It is a very important concept, and I hope that this video will be able to give you a very good example of basic understanding of scalar triple product. The idea behind this video would be to first introduce scalar triple product to you, and then do few problems on this topic. After that, there will be also a follow-up video in which we will go over more examples of scalar triple product. Okay, so what is a scalar triple product? Till now we have done dot product, which was A dot B. Then we have done cross product, which was A cross B. Now this says a scalar triple product. So the name suggests triple means there are three quantities: vector A, vector B, vector C, and it is scalar product. Like dot product was a scalar product, similarly this is also a scalar product, but it is a scalar triple product. So there will be three vector quantities A, B and C, and the output would be a scalar. Okay, so let us first discuss how we can get a scalar quantity out of three vectors. So let us say we have vector A, and we have vector B, and we have vector C. Now how can I get a scalar quantity out of this? Can I do A dot B dot C? So this would mean that, and let me put brackets here. If I do this, then this would mean A dot B is a scalar quantity, then I cannot dot it with C. Okay, so this is not possible. Can I do A cross B cross of C? This would mean that this is a vector quantity, and then I am taking a vector cross another vector. That will give me a vector output. This operation is not possible. This would give me a vector output, but we want a scalar output, so this is also not possible. We will also be discussing what kind of product is this, but that is a part of the next video. But this will give me a vector output, so this is not good for us. However, can we do something like this? A cross B dot C. This is a vector then dotted with a vector, and this gives a scalar output. This is a correct. Okay, so this is what we want to know. So scalar triple product is defined as A cross B dotted with C. Okay, so what does this mean? What does this mean? This means that if I know what is and this is dotted with right. So how can we then get the answer? If you basically do this, the expansion would be something like this. You can imagine that basically you will find I component and then multiply all of that by Cx. So rather than doing ijk separately, you can just put Cx, Cy, Cz in the determinant at the top. Okay, so this is an important property here which I have written down. Okay, now okay, you have your first dotting A cross B with A cross B dot C. Now can you see something else also which might or might not be that obvious? Basically we know that that A cross B dotted with C is equal to C dot A cross B, right? So A cross B dot C is equal to C cross A dot B. We know that because this is a dot product. This is a vector. So you just took the this. Let us call this vector D. Then D dot C is equal to C dot D, right? So all you're saying is A cross B dot C is equal to C cross C dot A cross B. We know this, okay? Also, there are some properties of determinant, which basically means that you can flip two determinants and then the answer would become a negative of that, and if you flip twice, then the answer would remain the same. So if you think, if I flip A and C, then A will come to the top and C will come to the bottom. Then if I flip A and B, then B will come to the middle, and so we will first flip A and C and then flip B and C, so it will become A, B, C. In other words, A cross B dotted with C can also be AX, AY, AZ, BX, BY, BZ, CX, CY, CZ, and this I have done by flipping row twice, flipping C row and A row, and then B row and C row. You will get this. However, if you think about this, here whatever was in the dot came at the top. Now if I want to write this down, now I can write this also as A dot B cross C, okay? A dot B cross C. So what I have done here, what I am saying is whatever was in the dot came at the top row. So whatever was in the dot came at the top row, the single vector came at the top row. Now I have written this down. So A cross B dot C is equal to A dot B cross C, and this is a super important property, like A cross B dot C is equal to A dot B cross C. In other words, you can flip the sign of A and B. So the first property that we have discussed was this, okay? And the second property that I want to discuss is, that I want to highlight, is this: A cross B dot C is equal to A dot B cross C. Third property, so A cross A dot B cross C is equal to A dot A cross B dot C, and sometimes this is written as A B C, okay? Sometimes this is written as A B C because dot and cross doesn't matter. It doesn't matter you are taking dot here or cross here, it will always come out to be fine. It will always be the same, okay? So I hope that this is making sense, that we first said this is a determinant, then we flipped the rows so that the value remains the same, and then because the top row was a dot alone vector, then we said A dot B cross C. So A cross B dot C is same as A dot B cross C, okay? And we also know that A cross B dot C is equal to C cross, and we also know that this is the same as, because this is A cross B dot C, so we can also write this as C dot A cross B, right? So we can, or C cross A dot B, right? This can also be written, or this can also be CAB, because now we are taking the associative property of dot. Similarly, now I can write this as B dot C cross A. I am taking the property of, I am flipping dots here again, and equal to, now I am changing, writing this as B cross C dot A, changing dot and cross, and this is B C A, okay? This is a very, very important property. What I'm trying to say here is A cross B dot C. So I hope this makes sense. You can change dot and cross, one thing, and then this seems to be a cyclic property. The cyclic property says that A should go to B, and then B should go to C, and then C should go to A. So what is happening is A, B, C, A, B and then C. So you can always think of it in cyclic, A, B, C. So the cycle is always A, B, C, and that means if as long as you have A, B, C written in the correct cycle, then the value remains the same. In other words, A, B, C is equal to C, A, B is equal to B, C, A. And I just want to highlight one thing after that this is equal to minus of ACB. So if you flip two things, so the cycle has broken now. It is not ABC, it is ACB. So you have broken the cycle and you have reversed the cycle. So rather than ABC, you are now going ACB. So that's why you have a negative sign. And you can check that if you flip just two rows, just B and C, only one row, if you exchange one time, then there is a negative sign in front of the determinant. So that is why there is a negative sign here. And now here you can again make the cycle. That this is equal to minus BAC. Again the cycle is now ACB, not ABC, and is equal to minus CBA. Okay. So this is a very, very important property. I hope that you are able to now understand what we are doing. So we discussed a lot of things very quickly. One thing, that this is a scalar product, A cross B dot C is a scalar product, because A cross B is a vector, and then you are dotting it with C. And then the second thing we discussed was you can flip the sign of dot and cross. That is because through the determinant property I showed that when you flip twice, you can basically see that A cross B dot C is equal to A dot B cross C. In the third property, you said there is a cyclic property of the whole system, and that we saw by exchanging the dot and cross. By exchanging, using the property of dot product, that A cross B dot C is equal to C dot A cross B. So there are a lot of things here. So you should take some time to just digest these things, because these things will be used in and out, and they are very, very important for the chapter of vectors. So please take your time to understand these things. Just very slowly go through writing these equations, and then you should be able to understand this. I don't think this is a very, very difficult concept to grasp, but for once you have to really understand it. Okay. So two things: you can exchange the sign of dot and cross, and then there is a cyclic property, and for A dot B cross C, you can just use a determinant. Okay, you can use a determinant. Now, the next thing that I want to discuss, like all other products, is the physical significance. The physical significance, and what is the physical significance of A cross B dot C? So what we have to realize is that this condition A dot B cross C, if this is 0, then A, B, C are coplanar. And I want to prove, so I have written it, so this is the first part of the significance, and I want to stress on this quite a lot, because this is something which you will use again a lot in questions. So what does this mean? What does this mean? So let us say you have two vector B and C here, then B cross C. So two vectors are always coplanar. Okay, so if you have two vectors like this, let us say you have two vectors like this, then you can always pass a plane through them, right? You can always pass a plane through these two vectors. So B and C are vectors, two vectors, and then you have pass a plane through them. Then there is the perpendicular vector. B cross C is a vector perpendicular to both B and C. This is something we have discussed in cross product. So if you cannot recall it, please go and check back the notes on cross product. And whenever there is B cross C, the vector which is, let's say, n, is perpendicular to both B and C. Now what we are saying is that this n vector is perpendicular to the plane of B and C. Now A dot n, because B cross C is n, because B cross C here we are saying, let's say B cross C is n, A dot n is 0. A dot n is 0, what does this mean? That A and n are perpendicular now. So if A and n are perpendicular to now, then A has to lie in the plane of B and C. So this means that A has to lie in the plane of B and C, or A, B, C are coplanar. And what does coplanar mean? Coplanar means that if there are three vectors, you can pass a plane through them. Okay, so two vectors you can always pass a plane through them, but if there are three vectors, let's say there are two vectors like this and one vector like this, you cannot pass a plane through them. Only two vectors you can pass a plane, but if there are three vectors, you can not always pass a plane through them. And when can you pass a plane through them? Whenever A dot B cross C is 0 or the scalar triple product is 0. And how are we explaining this? We are saying that B cross C is a vector which is perpendicular to both B and C, or is perpendicular to the plane of B and C. And when A dot n is 0, that means A and B cross C are perpendicular, because dot product is 0 whenever two vectors are perpendicular. So that forces A has to lie in the plane of B and C. Okay, this is very, very important, and I mean, you just have to just remember this, that whenever you see that two vectors are coplanar, just you should remember that the scalar triple product is 0. Also, you should remember this, that coplanarity also means that you can represent the third vector as a linear combination of the first two vectors. That is also a way to understand coplanarity. What is coplanarity? So when will this happen? When can you represent a vector as some linear combination of A and B? So let us say there is A and B, and there is a plane which passes through them. Then you are saying that you are stretching one vector or doing something to the like stretch L and M, like could be anything, any real values. Let us say you made one vector half, other vector double, and then now you are adding them. So you will basically be completing some sort of addition, and addition forces you to not leave that plane. So that is why these three things are coplanar. And you can also imagine, if I put C is equal to LA plus MB here, right? LA plus MB here, C here as LA plus MB, then if I take cross of B with B, it will become 0, right? And then it will basically become A dot B cross A, right? A dot B cross A, and then you can flip dot and cross, and it will become A cross A dot B, and dot cross of A with A will also be 0. I mean, you can check, you can just put it back here and check yourself that this will always come out to be 0. So coplanarity also, and you can also understand that coplanarity means that one vector can be written as a linear combination of the other two vectors, and that ABC is the scalar triple product ABC is 0. So I hope that this is sort of giving some insight to you what does scalar triple product mean. So dot product was the projection of a vector on the other, cross product was a vector perpendicular to both the vectors, and scalar triple product equal to 0 means a condition for coplanarity. Okay. Second thing that I just want you to learn as a formula, that is more like a formula, that if there is a parallelepiped, what is a parallelepiped? Is like it's like a rectangle, but rather than having perpendicular sides, it is just parallel. So it's like a 3D parallelogram. Okay, 3D parallelogram, and the volume of parallelepiped is ABC. If the three sides are A vector, B vector, C vector, then the volume of parallelepiped is ABC. There are a lot of proofs for this. I don't think you need to really understand the proofs. So this is like A vector is this entire side, C vector is this entire side, B vector is this entire side, then the volume of parallelepiped is ABC. Okay, and if there is a tetrahedron, so I will just write with these sides ABC, then tetrahedron would be ABC by 6. Okay. So I mean, if it's a little bit unclear to you, just do not worry too much about this. Just go back and look at some images of tetrahedron and parallelepiped, and just remember that the side, whenever sides are A, B and C, then the volume of parallelepiped is ABC and volume of tetrahedron is ABC by 6. Okay. So we have discussed, again, now let us recap whatever we have discussed. So this ends the property discussion of the scalar triple product. And what we have discussed is, if A dot B cross C, we can write it as a determinant. Okay. Then we also learned that you can flip dot and cross, and that is, I showed that by, if you flip to twice, the determinant twice, then you can get the same sign, and hence A cross B is equal to A dot B cross C. Then we learned about the cyclic property of ABC, and that there will be a minus sign whenever the cycle is broken or becomes reverse. And then we discussed two things about physical significance. Condition for coplanarity means that one vector is a linear combination of the other two vectors, and that is also expressed in terms of A dot B cross C is equal to 0, because B cross C is a vector perpendicular to the plane of B and C, and if A dot n is 0, that means A has to lie in the plane of B and C. And finally, if ABC are sides of parallelepiped and tetrahedron, then the volume is ABC and ABC by 6. Okay. So these are the properties that we have discussed. Please remember them, learn them. They should be on your fingertips whenever you see them. Okay. So now let us try to do some very quick problems, small problems, and the problems are, first problem. So let me create some clear demarcation. So the first problem is, if ABC are coplanar, what is the value of what is the value of 2a minus b, 2b minus c, and 2c minus a. Okay. So we have been told that there are three vectors ABC which are coplanar, and then we have been asked to find the value of some scalar triple product of linear combination of A and B and C. So there is one way to solve this problem, is that you take the cross of this. So I mean, you can just start taking cross and then taking dot and then trying to find something in terms of A, B and C. But my point here is really to make you understand what this means. So think about three vectors. Let's say A, B and C, and they are coplanar, So if you have two vectors like this, and you have the third vector like this, they are in a plane. Now what you are doing is, you are just taking a linear combination of these three vectors. Can you ever go out of the plane? Can you ever create a vector which is out of the plane? So for instance, if C is LA plus MB, because ABC are coplanar, that means LA plus MB, then 2A minus B is a linear combination of A and B. 2B minus C, because C is LA plus MB, is also a linear combination of A and B, and 2C minus A is also a linear combination of A and B. So even all these three vectors are just linear combination of A and B. So that means that they are in the same plane. So you don't even need to do anything. You don't even have to calculate. You can just directly write that this is equal to 0. Because if ABC are coplanar, then any linear combination of these vectors would also lie in the same plane. So these three vectors are just in the same plane. So you don't even need to worry about it. You just have to understand, okay, these three vectors are coplanar. So any linear combination of them has to be coplanar. So that means this is 0, which is a condition of scalar triple product. So I can bet that a lot of students here will try to solve this problem. They will start with ABC is 0, and then they will expand this using taking a cross here and a dot here, and then opening up the brackets and then trying to solve it somehow. But you don't even have to. You just have to understand that coplanarity means that the three vectors are in the same plane, or they can be expressed as a linear combination of each other, and any vector will also lie in the same plane. Okay. So I hope that this gives you some insight about scalar triple product. Okay, the second problem that I want to do is that what is the value of lambda such that lambda I plus j plus k comma I plus 2 lambda j plus k cap and I plus j plus k are coplanar. Okay, so what is the value of lambda such that these three vectors are coplanar? The question is begging you to say, remember the condition of coplanarity. The condition of coplanarity is A dot B cross C 0. That's it. So how can we write A dot B cross C? Is that we have discussed it is a determinant. So let us call this A vector, B vector and C vector. Then A dot B cross C is equal to lambda. So just take the coefficients lambda 1 1, 1 2 lambda, 1 and 1 1 1, and you have to make this equal to 0. Okay, and if you should be now, I hope with time you will become very quick with taking opening up determinants, and if you open up the determinant you will actually find that this is 2 lambda square minus 3 lambda plus 1 equal to 0. You can check that this is what it comes out, and that would give you the answer at lambda equal to 1 comma half. So this again in an objective type problem, this could be a multiple choice problem. And can we check the answer if we, what is lambda equal to 1 mean? So what does lambda equal to 1 and half mean here? Okay, so if lambda is equal to 1, then this becomes I plus j plus k, and this becomes I plus j plus k. So they are the same vector. So if they are the same vector, then that means that their cross will always be 0. So if they are the same vector, then basically this becomes two vectors which will obviously be coplanar. So rather than three vectors, if their two vectors are same, basically you are saying that there are only two vectors which are always coplanar. If lambda is half, then this becomes I plus j plus k. So and then these two become same. So again they become two vectors and they are always coplanar. Okay. So I hope that with this you are able to physically also understand the meaning of scalar triple product. So in this video we covered very important topic of scalar triple product. We discussed its properties, we discussed 4 properties, and then we did 2 examples to understand what is the meaning of scalar triple product and how to apply it. In the next video we will be discussing vector triple product, and I hope you enjoyed this video. Please check out the next video. Thank you.